Good afternoon, everyone. Today we have Dr. Tal Ezer here to present to us. He has a bachelor's in physics and mathematics, as well as a master's in atmospheric science and a Ph.D. in physical oceanography, all from FSU. Kind of ironic considering I'm wearing UM stuff today, but it is what it is. After that, he spent about 18 years at Princeton University developing ocean circulation models. And then after that, he moved to Old Dominion University in Norfolk, Virginia in about 2007, where he's currently a professor in the Department of Ocean and Earth Sciences. So his recent research there has focused on climate change, sea level rise, hurricanes, and flood protection. And today he'll be giving us a presentation on the interaction between climate change, hurricanes, the Gulf Stream, and the coast. So please join me in welcoming Dr. Tal Ezer.
Thank you very much. Great to be here again. And in sunny Florida. In my home institution, I expect 10 inches of snow this weekend. So it's nice to be here. Hopefully I'll be able to go back home next week. Anyway, so I'm going to talk about climate change, Gulf Stream, hurricanes, and many other things that seems to be relevant both to your area and our area. Now, a little bit about sea level rise. In many places, local sea level rise is rising faster than global sea level rise. Now, global sea level rise, the main two reasons for global sea level rise is thermal expansion of the water, become warmer, and melting the ice sheet and glaciers that add to the volume of the ocean. In addition, many places have land subsidence. In the area in the mid-Atlantic coast, for example, we still feel the impact from 20,000 years ago when glaciers covered North America and pushed the land down in Canada and North US, and in Virginia and North Carolina, the land was pushed up, and now the land is sinking back. That's what is called the GIA. In many other places, we have land sinking due to groundwater extraction, and many places around the Gulf of Mexico that were now the land subsidence. So the land is sinking at the same time that global ocean water is rising. There are also additional effects on sea level from oceanic and atmospheric dynamics, including the Gulf Stream, the Atlantic overturning circulation, other patterns like the North Atlantic Oscillation will affect the weather and so forth. Now, this land movement and the oceanic and atmospheric dynamics cause differences in different locations. So local sea level rise is different at different locations. The area that my research is focused is oceanic and atmospheric dynamics. And this is the area that probably least understood compared to other components of sea level rise. Just an example, in our area where I live in Norfolk, Virginia, when you see here, you see different estimates of sea level rise. The blue line is a global sea level from tide gauges around the globe. And the rate of the last century was about 1.5 millimeters per year. Over the last few decades, since about in the last 30 or 40 years or so, we have also satellite data that show about twice as fast sea level. That's the red satellite data. And if you look at the local data, the sea level in the green is rising much faster. So if you want to see what is a water level doing a storm surge, we have to take into account the global sea level rise, the local sea level rise that is faster, and then storm and tides. So the reason of local sea level rise is faster is because of the vertical land movement and the land sinking. In addition, we have acceleration in recent years due to oceanic and atmospheric dynamics I'm going to talk about later. So let's look at the hourly water level, for example, in Norfolk, Virginia. You can see that with sea level rising, we have more and more times where there is a threshold of either minor flood or major flood that become more frequent. And we do this calculation of how many hours per year we have above particular level. So this is a minor flooding happening in the streets, in our streets in Norfolk, when water level is about 1 foot above the high tide. And you can see in the past, most of these peaks related to major hurricanes. In recent years, because of sea level rise, even small storms still cause a lot of flooding. And if you look at the most flooded years, actually the most flooded years in history since observation started was last year, 2024, and 2025 was the second most flooded year. So if you look at the storm surge in Norfolk, these are the major storms that pass the area. And you can see that in the past, we had a period of 10 or 15 years with no major storms. And in recent years, we have this cluster of storms. Now, the largest storm surge actually happened in 1933, where the population was much less than today. Now, if you add the sea level rise, this line would move all the way there. So if we had the same storm that happened in 1933 today, it will be about 6 feet over the high tide. So this will be a disaster in our area if you add sea level rise. And there are also some decadal patterns more complicated with some years more flooding than others. If we look at the pattern of hurricanes, so this is a summary of how many days we see hurricanes and tropical storm in the area there. So if you look at the small hurricanes with category 1 and 2, that's the green bars, you see that in the past, we had maybe 10 days where we have category 1 and 2 hurricane over the area. Since the 1990s, we have much more, maybe around 20. If you look at the major storms, category 3 to 5, you see that in the past, until the 1990s, there were no more than about 3 days with such storms. Today we have about 10 or so with the red bar. So you see the increasing intensity of the hurricane. Just an example from the impact of one hurricane, Irene, that happened just last year. And what you see is a hurricane in the upper right panel did not make landfall, stayed offshore. But these are pictures that I took just a couple of blocks from where I live. And you can see all the flooding that happened in the street, even when the hurricane was far away, thousands of kilometers away. So there is some impact from remote influence. Now, when I look during the hurricane, what was actually the wind and the pressure during the hurricane, actually over our area, the wind was strong, but only about 1/5 of what it is near the eye of the storm. And the pressure reduced, but also a very small reduction. So what you see here is not the direct impact of the hurricane, but some indirect impact that I'm going to describe next. So if you look at the interaction of climate change in the coast, there are different combination of impact. You have the global climate change, the coastal sea level to rise that we talked about before. You also have impact on more intense hurricanes because of the sea surface temperature is warmer. We have also impact that we find from models and observations of slowing down of ocean circulation patterns, including the Gulf Stream. And the Gulf Stream, the water of the Gulf Stream provide engine for the hurricane. And the hurricanes cause storm surge. Now, on the other hand, hurricanes, when they pass over the Gulf Stream, that actually can weaken the Gulf Stream, and this will cause additional sea level rise. So what you see here is a combination of direct and indirect impact on the coast from many different directions. So it's quite complicated. If you want to study the coast, you have to take into account all these different components. So the coasts and the cities in particular Miami and also our area in Norfolk are subject to different sea level rise and acceleration in flooding. So for example, this is on the left, this is a street that lead to a museum, very famous art museum, that during high tides, the water can reach all the way to the steps of the museum. We have hurricanes and tropical storms that I mentioned. We also have winter storm and blizzards that, like the one that is expected along the coast of Virginia and Norfolk and other states this weekend. And we also have other climate effects, heat wave, fires, and other climate-related extreme weather events. Now, if you look at the flooding, there is seasonal pattern to the flood. If you look at hurricanes and tropical storms, you can see there is a peak in the fall around September, where this is the peak of the hurricane. If you look on the right plot, this is the annual monthly change in water level in the bars. And we have an additional impact of hurricane and tropical storm in the fall, and extra tropical and winter storms in the winter. In addition, we find out that in our area, there is also large signal from the annual and semi-annual tides, and also happen to be around September. So we have a combination of different components that all add to more flooding expected during the fall. So if you look at the seasonal variation in flooding, what you see is that there is a large change along the coast. If you look at the Gulf of Maine, for example, in Portland, Maine, more than 70% of the flooding occur during the winter and spring. When you go along the coast, you see that there are more and more flooding during the fall. So in Florida, for example, 75% of all the flooding occur during the fall, and I mentioned before why it occurs. So since we are sitting, our university is sitting here at the southern part of the Chesapeake Bay. Chesapeake Bay is the largest estuary in the US. So I did some research on Chesapeake Bay. Different tide gauges along the bay. And I was interested in how much is there any difference inside the bay between one place to another. When you look, for example, at the correlation of sea level between the lower bay in Norfolk and Baltimore in the upper. And when you look at the correlation, there is a positive correlation for all time scales, in particular the seasonal signal of the period of the 1 year. But for the longer period of decadal, they're actually in opposite direction. So it's a kind of a strange where one side of the bay sea level going up, the other side going down. And what we find out, the upper part is affected mostly by local wind. And there is something called the North Atlantic Oscillation. This is a pattern over the Atlantic Ocean that changes the wind pattern over the Atlantic Ocean. So the upper part is affected by wind and by this pattern. On the other hand, the lower part of the bay is affected by exchange with the Gulf streams that flow offshore and the Atlantic overturning circulation. So we have two sides of the same bay that are affected by different processes that happen to create this unusual pattern with over decadal timescales. Both sides move in opposite direction. When you look at the correlation, this is the correlation between sea level and the Atlantic overturning circulation. So we divided here into high frequency in the upper panel and low frequency in the lower panel. If you look at the high frequency oscillation, there is a negative correlation, significant correlation. Negative correlation between ocean circulation and water level, mean when circulation slows down, sea level would rise. On the other hand, if you look at the low frequency oscillation, it's completely different. First, there is a phase shift between the two when you look at the cross correlation. And there is a long period where sea level actually rise in Norfolk in the left, but drop in the other side. So we see how over a long period of time, sea level may behave in different places in a different way. When you look at the spectral energy of the sea level between the two locations, you can see the red one is the energy of sea level in Baltimore in the upper bay, and mostly the highest energy is during the seasonal cycle, about a period of about 1 year. On the other hand, if you look at the lower frequency oscillation on the right, you see that it's much more energy in the lower bay in Norfolk. And this is another indication that there is a low frequency oscillation coming from the Atlantic Ocean because Norfolk is close to the mouth of the bay, so it is connected to the Atlantic Ocean. One of the impacts on the coast comes from the Gulf Stream. So what you see here, the red is a warm water coming from the Gulf Stream. You see that it changes all the time. So this is quite challenging to measure and study the Gulf Stream where it is changing all the time. If you look at the coast and Chesapeake Bay, you see that at the same time when the Gulf Stream meanders and shed eddies and have all these variations, also the variation of temperature happen inside the bay. So how can the Gulf Stream affect coastal sea level? The very strong current. And the reason is behind it is basic physical oceanography, something called the geostrophic balance. How many of you heard about it? Okay, so this is basic physical oceanography, that whenever you have a slope, like what's the Gulf Stream, it's proportional to the flow. So what happens if you sail from the US coast to Bermuda, for example, you actually go uphill about 1 to 1.5 meters. So the Gulf Stream actually keeps the water in our side along the US coast lower than what it would have been without it. So what happened when the Gulf Stream slowed down, this slope changed and sea level would rise along the coast. So that's the basic physical idea behind it. Why the Gulf Stream slowed down? There's a long-term change due to climate change. There are predictions that due to climate change, ocean circulation will slow down. There are also short-term variation, daily variation in the Florida current, different seasonal cycle, hurricane, and so forth. Now, the Gulf Stream is also part of this Atlantic meridional overturning circulation, or AMO. Basically, what happened, the Gulf Stream brings warm water from low latitude to high latitude, then the water cools down, and it becomes more dense, and they sink and create this circulation. But what happened under warmer climate scenarios? We have a melting of ice in high latitudes. The water is also warmer, so they are not as dense, so they don't sink as fast. They don't sink as fast, the whole circulation slows down, and the Gulf Stream also slows down. If the Gulf Stream slows down, as I mentioned before, sea level would rise along the coast. So that's the connection between climate change, large-scale climate change over the whole Atlantic Ocean and coastal sea level along our coast. And there are several studies that actually found that sea level, that Atlantic overturning circulation is slowing down in recent years. We only have direct observation since 2004. But there are some models that predict further decline in ocean circulation. And even in the observations that they have a relatively short period of observation, there were periods during 2009, 2010 of decline, large decline in the overturning circulation that created, actually, there were several years with unusual flooding and higher than normal water level along the US coast during this period. Since observations are relatively short, only about 20 years, if you want to know if there is a decline over a long period of time, we need some other methods. Here is one of my early paper where the key line is kind of a reconstruction of the Atlantic overturning circulation using the sea level. And we can see that there is a general decline over years. The red line is only the recent observations. But we see that there are some periods where there is a even larger decline in ocean circulation. One was during the 60s and 70s, which is quite similar to what happened today. At the time, people didn't fully understand why they declined. I don't know if all people here remember, there was a time when people said that the new ice age is coming. There were some stories in the news that new ice age is coming because all the ocean circulation is slowing down. And now we know that it's part of this decadal pattern. And at the same time, during the 60s and 70s, sea level also was higher than normal during this period. Now, when we compare water level in different locations around the Chesapeake Bay in the Atlantic Ocean, we see that they work on longer period of time together on this decadal variation. When you look at satellite data of the strength of the Gulf Stream, we found out whenever there is a period when the Gulf Stream slowed down, we have a period of a few years of higher than normal sea level. Another period, another one. In this period, there was a large decline in the Gulf Stream, and then there was acceleration in sea level. And there is a correlation of about 0.85 between the long-term changes in the Gulf Stream and sea level. So the Gulf Stream also interact with tropical storms and hurricanes, which are important for sea level and flooding. So here is an example from one Hurricane Isabel in 2003, which created the second largest storm surge in Norfolk there. And so there was a very large storm surge, about 1.5 meters with high tide. But it lasted only a very short period of time, of less than a day. On the other hand, another hurricane, Hurricane Joaquin, in 2018, it stayed offshore for a long period of time. It did not make landfall, but still, water level created flooding almost every high tide for a period of 2 weeks. So this is another example of indirect influence of storm that stayed offshore, but it did affect coastal sea level, and we found out that the connection is the Gulf Stream. So here is a picture that I took during this Hurricane Joaquin, where the hurricane was actually thousands of miles away from the coast. We can see the relation to the Gulf Stream. So what happened? The hurricane was away from the coast, but it was close enough to the Gulf Stream to slow it down. You look at the blue line here. This is a measurement of the strength of the Florida current from a cable. There is a cable from Miami to the Bahamas that measures the transport across the Florida Strait. And you can see large decline when the hurricane was in the area. And thousands of miles away, we see this flooding, long period of flooding every high tide. This is the upper part of the. Another one was Hurricane Matthew, if you remember. There was a decline of the Gulf Stream by 50%. And then we had several weeks of flooding and high tide in our area. There were also two smaller storms before that. In each case, we had a few days of flooding. Another case was Hurricane Dorian. Again, Hurricane Dorian actually caused the weakest flow on record. They measured the transport of the Gulf Stream since the 1980s. And this was the case where they had the weakest Gulf Stream since they started measurements. And again, this period of time, a few days after the decline in the flow of the Florida current, we had this period of a few days of flooding. Now, how can a hurricane slow down a massive current like the Gulf Stream? When a storm is close to the Gulf Stream, there is a simulation from NOAA of one of the storms. First, the wind is blowing against the current. There's also a lot of heat loss from the warm water, and the intense mixing by waves and turbulence that cools the water. The water cool down, it affects the warm Gulf Stream. You can see the Gulf Stream is almost disconnected here when the hurricane was nearby. So here is some simulation of the hurricane, of the velocity across the Florida current. And you can see before the hurricane, there's most of the velocity in the upper layers, and then you see the deep mixing that happened in the right side after the hurricane. So here is the wind during Hurricane Matthew, and you can see how the wind propagates along the coast, and then the hurricane actually moved away from the coast. This is a simulation of the storm surge. See, the red is the water level going up, and the black lines are the wind. So now the wind is going away from the coast. You see it will play again. And you can see the back of the hurricane, actually the water goes down. That's the blue one, because the wind is pushing water away from the coast in the back of the hurricane. It's again, you can see how the hurricane propagates offshore, but still affected the coast. Now the storm moved away from the coast. And the interesting thing is that 12 days after the hurricane, when the storm was already away from the coast, the entire coast from Florida to past New Jersey and over to New York, from the red, remain high even 12 days after the hurricane. So this is a kind of a new finding that hurricane can have a long-term effect besides the direct impact that it has. Especially in the Chesapeake Bay, you see the high waters that remain there, and we had a lot of flooding. And we look at satellite altimeter data that measure variation in the water level. This is the upper part is a week before the hurricane. You can see it's all these eddies, and that that's how it looks in normal day. And then after a week after the hurricane, you can see the path of the Gulf Stream. So along the Gulf Stream, this is a sign the Gulf Stream slowed down, because you can see this red mean that the part of near the coast along the Gulf Stream, water level remain high, and you can see it's also red along the coast. So this is also evidence from satellite of this indirect impact. So what is the impact of the hurricane track? So we wonder, because the hurricanes can vary in their tracks, closer to the coast or farther away from the coast. So we decided to do some computer simulations of the impact of the track of the hurricane. What you see here on the upper part, it was a real wind speed during the hurricane, and the lower part is the simulation of the Hurricane Matthew. And then on the right, we moved the track of the hurricane up to 600 kilometers away from the coast, and we want to see what is the impact when the track is away from the coast. So here is a different location of the track. The top left is the original track, and then the other one when you move it away from the coast. So this is after day 8, and you can see this blue is mixing near the eye of the storm. And then, so this is the cooling effect of the storm. After a while, this is after 12 days, now you see kind of a mess, because the interaction of this hurricane with the Gulf Stream created all these large variations. So now actually you don't see much of the impact of how far from the coast the hurricane was. So even hurricanes that were quite far from the coast created this mass cooling. Even some places a little bit of warming because of motion of the Gulf Stream. And then after 30 days, now the Gulf Stream start to recover. So warm water coming here from the south start to recover. But keep in mind that the recovery is relatively slow. Hurricane cool the ocean fast, but this takes a long time, several weeks, for warm water to reach to moves all the way along the coastline. So when you look at, so each line is one of these different experiments with different tracks. So in all of them, when the hurricane was over the area, we have this weakening. So they tell you how intense is the Gulf Stream. So the dashed line is a normal one at the beginning, and you can see the big drop in the Gulf Stream strength in all the different tracks. But then, so this is pretty fast, happened within days. But then you see that all the different tracks, it takes several weeks, and the Gulf Stream remain weak for several weeks. That we have seen before. So we have a weak Gulf Stream for several weeks, and as I mentioned before, weak Gulf Stream means higher water level along the coast. That's why we have several weeks of high water level and more flooding even after a storm disappeared. A little bit more about the area in some other data. There are a lot of people living in the area, just the mid-Atlantic area, about 60 million people live there. And we wanted to look at some other data. One of the sources of data is a high-frequency radar. There are several radars located along the coast. This is an example from the mouth of the Chesapeake Bay. And what you see is mostly the tidal currents. These are operating almost in real time along the coast in several places. There are actually several locations where we can measure surface current with this high-frequency radar. And in this paper, I compared 3 different estuaries, major estuaries, the New York Bay, the Delaware Bay, and the Chesapeake Bay. And what we found out why we did the 3 different bays, they are quite separate. Each one has their own characteristic and dynamics. But we found out that there are some common characteristics to all 3 bays, which indicate that there is some common influence from the Atlantic Ocean. And since we have a significant correlation between the 3, it means that there is some signal in the Atlantic Ocean that affect separate estuaries. When you see here, this is the actual combination. Each color represents different bay. And what we see is there are these extreme cases where several bays have this unusual flow out of the bay. And now during the largest peaks there in January 2019, 20, 22, 23, all these peaks, I checked the map, the weather map, were cases where we have big winter storms. So when you have big winter storms, it's actually stronger than usual flow out of the bays. All 3 bays, we have this strong flow out of the bay. Also precipitation and melted ice. On the other hand, you have these peaks where you have less flow out of the bay, more flow into the bay. And all these cases where I checked the location and the timing are due to hurricanes, some of the hurricanes that I mentioned before. So during hurricanes, we see larger flow into the bays. So these are the influence that you see from the Atlantic Ocean and the weather systems that affect the entire coast. Another impact we wanted to check, I mentioned before, a pattern called North Atlantic Oscillation. This is a large pattern of the atmosphere and pressure, atmospheric pressure over the entire Atlantic Ocean. This affects, for example, storm tracks over the US. And when we compare the North Atlantic Oscillation to the flow from the 3 bays, we see that there is a significant correlation between them. So when this NAO, North Atlantic Oscillation Index, is high, it means that this pattern of wind moves to the north. And then this is when we have more stronger flow out of the bays. It's a positive. On the other hand, when this pattern has a low index, the pattern of wind moved to the south, and you can see the influence on the base. So continuing with this surface current from high frequency radar, there are actually more than 20 radars operated along the coast. And you can combine them to get actually a picture of the surface current along the coast. And you wanted to see if there is any influence from the Gulf Stream on the coastal current. Now, most study, 90% of the studies of coastal currents assume that all the coastal surface currents are wind-driven, and they neglect any other influence. So I want to see how the Gulf Stream may influence the surface current. Now, this radar only captured very small part of the Gulf Stream near Cape Hatteras. This is Cape Hatteras, North Carolina. It's the only place where the Gulf Stream flow very close to the coast. But when we do some analysis, we do analysis called the EOF, empirical orthogonal function analysis. This analysis on the right capture patterns. And this is quite useful for analysis, for example, weather systems and oceanic patterns. What we found out that there are some patterns that focus on this area around the Gulf Stream, and they show you how the influence of the Gulf Stream on currents near this area. If you look at the average velocity from these radars over the entire area, we see these peaks, A, B, C, and D. Each one of them is a major storm. So when we look at the coastal surface currents,
I think one of the doors should be open.
so when we look at the surface currents, the upper graph is during one of these storms. You can see the surface current can be almost as strong as 1 meter per second, very strong during the storm. And then after the storm, you see that they return to about 1/10 of it during the storm. So this data is very useful to capture storms and their influence on the coast. Another pattern that we found involved the velocity in the north and the part of the mid-Atlantic. So the red and blue means that they are in opposite phase. So this means that when this pattern is in positive phase, the north part has strong currents and the low part have weak currents. And this is directly related to the wind. So you can see when it's in a positive phase, you see on the right upper part, then there is a strong wind coming from the northwest. With this pattern is in the negative, the wind is much weaker. So this is a mode that shows us the impact of the wind. Now another mode that relates directly to the Gulf Stream affects the flow along the shelf break current. So this pattern shows that when offshore along the shelf break current is stronger, then the coast flow along the coast is weaker and opposite. And what you find out when this pattern is in a positive phase, that's when the Gulf Stream is far away. This is the upper right panel, far away from the coast. And then when it's in the negative phase, the Gulf Stream meander, get closer to the coast. And actually, there are some studies of biology that show that when the Gulf Stream get too close to the coast, it can have a significant impact on the ecosystem and fisheries. For example, in the Gulf of Maine, when the water gets too warm, it affects the lobster industry. So the variation in the Gulf Stream are kind of important, not only for physical oceanography, but also for biological, marine biology, and fisheries, and other aspects.
But here, when the Gulf Stream comes close, everybody goes out and tries to catch big fish. The Gulf Stream comes close and we get a really good fishing season.
Good to know. Okay, so here, in addition to the radar, coastal radar that show you the surface velocity, I try to compare it with satellite data on the right side, satellite altimeter data. The coastal high frequency radar doesn't extend much further, so it doesn't really capture the offshore. On the other hand, the altimeter data capture quite nicely the location of the Gulf Stream. So here we compare, for example, two periods. One in April, where the Gulf Stream position, you see the Gulf Stream position and Gulf Stream velocity. When the Gulf Stream was farther south but stronger, and then at the bottom, this is another period, B, where the Gulf Stream moved farther to the north, but was much weaker. And what you see when you compare these two data sets, so the altimeter data is very useful to capture all the changes in circulation offshore near the Gulf Stream. But if you look closely near the coast, it looks quite chaotic and very noisy. So it's not very useful in this case to get all the variation, at least this type of altimeter data that is mostly meant to look at ocean circulation offshore. So this suggests that maybe combination of the two data sources, satellite data and coastal radars, can produce a better estimate of the currents than just using each one separately. So when we want to know what is the contribution of for surface current from the wind versus the Gulf Stream. So on the left, this is the monthly Gulf Stream offshore current correlation. And you can see that there is a large variation. This is the correlation coefficient. So even when years, some years there is more influence from the Gulf Stream, both the Gulf Stream position and the speed, and some years you don't have much correlation. So it's the influence of the Gulf Stream is very complicated. So some years maybe there is more influence than another. On the right side, this is a wind influence. So the wind has much higher correlations, but again, you see large variation between one year to another. And some years there's more influence of the wind on the offshore component, some along the alongshore component. But in general, what we found that the wind contribute about 50 to 80% of the surface current variability, compared to the Gulf Stream, which contribute about 10 to 35%. So even though the Gulf Stream influence was mostly neglected in past studies, it's still not negligible and can have sometimes have strong influence, like we have here about the fisheries and other important for sea level, as I mentioned before, and currents. So in summary, the Gulf Stream contributes to coastal sea level and coastal currents in different ways through interaction with the Atlantic overturning circulation, with the Atlantic Ocean, interaction with the change in the wind pattern, interaction with hurricanes and tropical storms and winter storms. So we need to take into account when we study the coast, all these different combinations, direct influence as well as indirect influence through all these connections. So better understanding of this interaction is needed to improve future projection of climate change and impact like sea level rise and flood prediction. So with flood prediction, you may need to include several different components like I mentioned here. So if you're interested, here are some of the papers that the results are from, and if you're interested in more communication, I have that right here. Thank you very much.